All right, so very quick recap of what we have been doing so far. We're going to do a little more practice in ODEs. So we have concerned ourselves with an initial value problem that is basically an ordinary differential equation in the form dy dx is equal to f of xy. Okay? So the main problem here is that I might have some dependence here not only on the variable x, but also y. So this might be problematic to integrate. Okay? So if it's reasonable form, if it's only dependent on x, then I can integrate easily and find an analytical solution. I don't need numerical methods. Possibly it could be in a simpler form so that I can do, for instance, separation of variables or something like that you have learned in your ODE class, or it's Math 427J, something like that, yeah? Okay, so basically you would then find a formula solution for function y, and you are able then to define that function everywhere. In numerical methods, now basically 98% of problems out there don't really have an analytical solution. Okay? And that's probably a little bit of a skewed number because I'm here trying to motivate numerical methods, but a large class of problems does not have analytical solution. More importantly, it might not even be a proper function, it might be data. Okay? So you might be working with the well-log data or something of that sort that you're fitting into a functional form. Possibly you can do some curve fitting to actually get a function, but you don't necessarily have a nice form here on the right-hand side. And in that case, you need numerical methods. So what do? We actually do need, for this is an initial value problem, so I actually have to start from a value that I know at a point. Okay? And then I'm gonna discretize an interval where I'm interested in solving things. And I'm going to simply step forward as follows. My value at the next point, so h is my discretization step, my value at the next point is the value of the previous step plus some slope times h. And this is the general form of what we actually call Runge-Kutta methods. So we started really simple. Our first attempt was Euler method, which basically I start from this is my xi, this is my yi value. This is my slope here is precisely dy dx, so I know the slope, it's actually f of xy, right? So this slope takes me to this point, and this is my next value, yi plus 1. And I keep stepping like this. As we commented, first, you have some error in the previously computed solution that you propagate forward, and you're also obviously here making an error, this much of an error, right? So you keep pushing that forward. Nevertheless, as my h gets smaller, I get better. So we had this, let's just quickly go to the code we had for a simple problem. And I'm executing, everybody has the Euler code by now? So I'm executing the same example. I believe I shared this example. So I'm going to execute everything, but we're going to focus on the Euler method here. So this is my example Euler method. This is a function that we programmed. So basically I take this previous value in a for loop plus f, this is my slope, f of x, y at this previous point times h, and I simply do that in a for loop, I'm done. So this is a simpler program compared to most of the ones we've seen. And of course I have to have my function f programmed for this. So if I do an example, I'm going to execute this one. And type it in. So this is my Euler method. If my h is 0.5, which is pretty coarse over here, okay? I'm gonna make a pretty big error. My analytical solution is in black. This was a simple example we worked on in class, so I have an analytical solution, and this is how I test methods anyway. Okay. So this is the error I'm making. However, as I reduce my step size h, I get better and better, and I'm approaching this analytical solution. Okay. This is the main idea. Everything else we've done so far, we're basically attempting to improve these methods. Okay? So first improvement was so-called Hoynes method. Okay? This method simply says, all right, well, instead of taking this major slope here that I was taking to begin with, I'm going to take slope at this point. I'm going to sort of pre-compute my next point and find the slope there and just average the two. And this should actually get me a little more on track. And indeed, this is what also executed here in the same script. We saw that basically with this Hoynes method, for the same step, h is 0.5, I get closer to my analytical solution. Okay. And I can actually iterate and do this iteration a number of times. I can have sort of an internal loop going on as many times as I want to achieve better accuracy. Okay, so this is fine-tuning the method. However, if you actually have time to iterate, I'd better then go with Runge-Kutta method. Okay. This method, in short, basically tries to estimate 4 slopes, and we call them K1, K2, K3, K4. Okay. And it finds a weighted sum of those slopes as the ultimate slope taken. Now, these numbers are not taken out of thin air. They're actually taken, we didn't go through that process, but they're taken from the Taylor series and attempting to cancel first all of the up to the 4th order terms in Taylor series. And because of that, I get a major improvement in accuracy. I'm going to go back to the code and show that. Okay, that was in this figure 2. So basically, when I look at Runge-Kutta method, which is here in this magenta color, I'm right on the money. This is what's called 4th order accuracy. Okay. So does everybody have a code, Runge-Kutta? I'll show what we came up with last time. So I chose to name this value at the midpoint, so taking first slope halfway to a new point y and evaluate it. If at that point I chose to call it a different value. Most of you have probably programmed something like this, and that might be more similar to the formulas we've seen. So I'm just going to modify the code quickly to resemble formulas written on the screen. So these are my 4 slopes. Okay. And then my ultimate slope is the weighted average of all of them. And that's the slope I take to my next step. Okay. And it is a little more involved method. Of course, I have 4 slopes to compute, or rather 5 altogether, compared to Euler's method, but I get much better accuracy. Okay? So just to get a practice of this, since it is a last week and we have homework due on Friday, let's open up that homework. And I'm gonna go quickly. I think I have it in my downloads. So I would like you to here we go. So in homework, okay, you're given two problems. They're slightly different problems from what we had before. Oh, there we go. And let's take the first one, okay? You will derive the analytical solution yourself. Which method are you going to do here? Separable. If I take y out, I have a function of x, so I can divide by y and figure that out. Okay? So you can do that analytical solution on your own, but let's actually now, you essentially have the code for Euler's, Hoynes, and Runge-Kutta method. Let's apply the code we've so far done, and let's solve this problem A right now. Okay? And I'm going to first walk around. And you can simply, this new example, you can call something else. Let's say save as. My save button has disappeared.
I think it lets you save in the editor.
Editor? Okay, thank you. So I'm just gonna call this homework 10, problem 1A, homework 10. So what's going to differ is analytical solution, which we don't have right now. Okay, you're going to figure it out. But all we need is this Euler method with DH is 0.5, 0.25. And I need to modify this to be, I'm going to also call it 1A. So this has to be somehow modified to actually solve the problem you have in the homework. What is going to be changed? What's the only thing you're changing? So let's get going. So just this function. And what's good about having this function is that we have it programmed so it works for any starting point x1, y1. That's our initial value, right? Value of the function at x1 is y1. And xn is your endpoint of the interval for x. So the function is already generalized, really, except for the value of the function. We did not go there in this class, but technically you could actually pass to this function a handle to a function from the outside. So function could be a variable as well, but I just didn't want to go into that in class. This is just fine. And we already programmed it as our initial function was not a function of y, but we just put it more general. So we're ready just to replace this. which is this mu function? How do you call this mu? Well, that's somewhere. Yeah. Indicate somewhere that it's somewhere because you have three methods. Yeah. Perfect. Does anybody manage to compare them all? If you happen to be bored with 1A, may as well tackle 1B and have the homework pretty much solved, or do the analytical solution. Yes, that's your initial value. So initial value here is y1 is equal to what? So what is y1? So x1 is 1, we are solving on interval 1 to 5. And y1 is also 1. It's actually the same as the one we got 0, 1 as the starting point of the previous problem. You like analytical solutions, all right, go find it. Yes. So you're solving. If you needed to solve an analytical problem to get there, then remove the possible variable. The only reason why you need an analytical solution here is to compare. But most of the time in real life, you don't have an analytical solution to compare. So you do that with a couple of known problems to validate yourself. Okay. And then use it occasionally. So I want to see that comparison plot. And with a Rangekara. Yes. So that example, that's kind of like a similar script like that. You just remove what you don't. But that's basically the foundation. Yes, so we don't have an analytical solution here, so we can Oh, you did? Oh, okay. Oh, so then the you know what happened? So here I needed something to start with this. Some very fine way. Just to we don't have convergence here. 10 to the 240. What is the maximum? What is the maximum real number? Which is exponent is 340 or something? Yeah. You're almost there. common mistake? Oh. It's a leftover. Who were you trying to tell what class you're teaching?
I'm teaching in this class.
Okay. Do you want me to leave?
No, that was for teaching language.
Oh, hi. So we're in 310. You noticed? Okay. So my problem here, dy dx, is 4yx cubed minus yx minus 2y. This is your function f of xy. This is what you replace in your Euler Method Runge-Kutta endpoints. This, not the analytical solution. Analytical solution is already a solution for y. So you do analytical solution, which is exponential something, 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 only to check the solution of this. But the whole point is that you don't have analytical solution most of the time, and you're looking for it using numerical methods.
So when I tried to plot the analytical solutions I tried to do at first, it did not show up on the graph for that reason.
Okay, I can check your specific problem. Yeah. But this is where you replace function f with this. And basically we had Euler's method, Hoynes, and Runge-Kutta's So those three methods, you already have them programmed. The only line that you're changing is this one. And then it should. And then it's just plotting it with these numbers, which are 1 to 5, and each number. Look at your specific problem. And then you can walk around others. Let's see. Let's reduce. How about we do one, just two. Okay. But the problem is still it's going to this is function plus. So reason is why
Yeah, I was confused about that as well. So like I closed it so we could
so just say why from 0 to 1. Oh, that's all right. Sorry. What is a good value? 10 for the value? Oh. No, the graph is why is it doing that? It goes really quickly.
So then is it my analytical solution? No, that's saying what I did is I took the
Oh, okay, each of the 1.5, yeah. Well, it's a little.
That's what it's giving me, like a 1.7.
Yeah, that's what I'm getting.
I would also just limit it to 1, 2. So let's change this from 1, 5 to 1, 2 for this. It's exponential function, so it goes really quickly. You need here a dot. Remember the vectorization. Don't forget vectorization.
So do you want to switch off?
You can do it analytical later. Did you plot it? There's issues plotting analytical solutions that grows really quickly. So you can just reduce the work on 1, 2 to just make that. Oh. So, did everybody get at least the first comparison plot for the homework? No? Let's get there and then we'll move on. Discretization is h 25 to 25. Yeah, so just do it on 1, 2, 1, 5.
So then you're going to get that.
Mm-hmm.
So it's going to be what is it?
Yep. Okay, I'm gonna slightly move on so you got started on the homework, you know what you need to do. And basically just repeat it for the second problem as well. Let's just now wrap up our differential equations with just a quick comment in, so we've done fourth order Runge-Kutta. I mentioned last time that you can have a whole range of second order methods. And really what changes is what type of slopes are you averaging and getting your ultimate slope that you take. Now, we're gonna move on to systems of ODEs, and that's gonna be our last ODE topic. So often you actually have multiple things depending on each other. And a classical problem for that is so-called predator-prey problems. So essential rate of change in the population of predators and prey, for instance here lions and gazelles, but you can take anything else, okay? And it could be fictional predator and prey, it could be anything that kind of depends on having something else around, goes like this. So I have a certain birth rate and a certain death rate, okay? And as far as lions go, nobody eats lions other than people maybe, so people are missing in this equation, okay? But let's say that we have a system just with lions and gazelles. In that system, basically I have number of lions and how much food they have, that's number of gazelles, times a birth rate, okay? That's what basically gets that population growing, and what gets it reducing is basically simply death rate of lions. Okay? And if I had people here, I would be here minus people killing rate, right? Of people coming and killing the lion. Now, as far as gazelles go, okay, I have birth rate of gazelles times their number, so there's a certain rate per population. But their death depends on number of lions. What kills them is the lions. So these two are coupled together, okay? And I have to solve them simultaneously. Now, for such system of equations, so basically I now, instead of having dy dt is a function of y and t, and I have now two of them. So I have dy dt is a function of y, but also something else, z and t. And dz dt is another function, also depending on both of those functions and possibly time in itself. So we can actually apply the very same methods that we've been working on. So this is basically, if I had two ODEs like this, and I might have more, it doesn't really matter how many. What I'm going to do, okay, I'm going to use, let's say that I'm using Euler's method. Okay, I'm going to use Euler's method on this and this simultaneously. So my new value yi plus 1 at a point, I'm going to start from a previous value times, this is my Euler's method, but this is this first function of whatever previous solution, previous step solution I have, times h, and zi plus 1 is zi plus f2 of this times h. Okay. Cool. If I had a better method, I have learned that fourth order method is better. Okay. I can actually do this with the fourth order method. So basically I need all of these slopes for my y solution and then 4 slopes for z. So it's a little bit of writing, but it's the same approach that we used for the single equation. Okay? So systems, we approach the same. So let's actually do an example. Let's do d squared y dt squared plus 4y is equal to 0. I'm going to actually switch to writing. Okay. So let's actually see one example. System needs to recognize something. Okay. Okay. All right. So this is an equation that I'm solving, and I'm actually I'm going to figure out a way to solve it using systems. So what can you tell me about this equation? What's the order? Second order. Do I know how to solve those using what we learned, what we just reviewed right now? Is it in the form dy dt is equal to f of yt? No? Let's do a trick. Well, this is d dt of dy dt, right? Plus 4y. Everybody agrees with me? What if I say, hey, z of t is dy dt, also a function of t. What does this become then? d z. I heard that, however faintly. dz dt plus 4y is equal to 0. So I have this, I have this. If I rewrite it a little, just clean it up, dy dt is equal to z, and my dz dt is equal to negative 4y. This is a system of coupled ordinary differential equations. Why are they coupled? Because y depends on z, which is another function, okay? And dz dt, the rate of change of z, depends on y. Same as those predator and prey, gazelles and lions. Okay? And what is my initial value? Well, y of 0 is 1. That's what's given here. And what is z of 0? So I am in the form of a coupled system. And this is what I would call f of t, y, z, f1, and f2 of t, y, z, right? Some function of the variable t, as well as the both functions that I'm trying to look for, y and z in this case. So can you write down on a piece of paper Euler method for this? In my iteration, I'll just write down that formula. Just as a reminder, if I had a generic problem, dy dx is equal to f of xy, then the problem was yi plus 1 is yi plus f of xi yi h. That was my Euler method for a single equation. And for multiple equations, I do the same approach, just both at the same time. And I possibly depend on two functions. I'm going to assume n is my size of the problem, right? So then y of I is equal to what? Or I plus 1, we can do it this way. Y of I plus? So f1 of t, I'm just going to write it down, of t of I, y of I, z of I. And I have f1 programmed somewhere, hopefully. Okay. What is f1 in this case? Simply z. So this is basically equivalent to, I'm just going to put as a comment, y of I plus 1 is y of I plus simply z of I times h. Okay. what is my z of I plus 1? Times h. And as a comment, well, f2 is simple in this case, so z of I plus 1 is simply z of I we have 1% away. Good job. Y of I times h. So my function is minus 4y. Everybody sees it? Question? Questions? No? And of course, before here, I will have to actually get myself, well, t of I, though actually doesn't play as part of this function at all. But the range of t's, a starting value, I have to have a starting value defined. So basically, y of 1 and z of 1 have to be initialized, right? Is 1 and z of 1. Again, this is z of 1 as in z of the first value, yeah? The first value at the first point. So I cannot write z of 0. Okay. So now you know, and every other method that you know, you can basically replace. So this is Euler's method. It's the simplest one. But we can replace this with Hoynes, with Runge-Kutta, and anything is fair game. So on your exam, most likely not, I'm going to give you one of these methods. It doesn't even matter that you know which one it's going to be ahead of time, and I'm going to ask you to implement it. Maybe on a system, maybe for a single equation. Okay. So that's a fair game exam question.
So one of these questions would be code, right, and not actually how you do it, right?
Yeah, most likely no. Since I'll let Math 427 test your analytical skills. Okay, that's not the objective of this class. But granted, a lot of you are taking it at the same time, so you'll be ready. You'll be ready to do it regardless. But I do expect you to know the numerical methods. Well, that essentially wraps up our differential equations. What is left in the class is integration. We're going to do only once introductory, sort of half of a class really makes sense. And then after that there will be course evaluation. So I do ask you to come because after you complete the course evaluation, then you will get a quiz grade for that. The university wants a lot of course evaluation complete. Course evaluation is completed, so I'm going to motivate you by giving you this grade. So that's about it for today. We're going to, again, I'm going to have office hours 11 till 1 today. Your office hours tomorrow are?
3 to 6. 3:20 to 4:30.
Oh, 3:20 to 4:50, very exactly. And possibly over. Everybody has a pair for their project. So I have one group of 3, and that's it. They're not supposed to be multiple groups of 3, just because we are odd numbers. All right. Well, as Stephen said, it's.
Are you going to upload the ODE content in this?
Yes, I am. I'm going to do that right now.
Also, one more question. One, please do semi-log y to plot it because it's exponential, so
It grows really quickly.
so do semi-log y.